Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. This is for Integrated Math 3 as we cover questions on polynomials, distributing, and factoring. At least that's what I expect to see. I got 11 questions in store for you here from my students where they ask questions and I answer them in a free response manner, what have you. I haven't seen the questions yet. I'm going to copied and pasted them in. I hit the record button and we're going to go straight to it. Questions are asked and answered in the order which they are received. I don't know if I asked them to try and not give examples. I try and give the examples as needed within the questions. They should be content based on polynomials, so they are ready for their next upcoming quiz. So let's just jump straight into it right here. Let's see what our question bank consists of. Let's start with the first question, which says, how does the even odd thing work when factoring and trying to guess and check? So if you haven't seen me do quadratic trinomial factoring, I use a mental guess and check strategy with it. I FOIL things out until it works. I actually try and multiply things out. And my goal is to not guess every factor under the sun until it works. My goal is to reduce my factorization guessing, right? I guess as little as I have to, so I save myself time. I land on a right answer a lot easier by doing that. Let me, before I answer the question, let me kind of talk about what I mean by what I'm doing with it. So if I took, I got to come up with one here. Let's do 4x squared minus 8x minus 21 right here. Now, I already know what this factors to because I had to make something that was factorable here. What my guess and check method would consist of, assuming it is factorable, this is some sort of binomial times binomial, and then the first two terms would multiply to become 4x squared, some sort of x times x, but the coefficients are either 4x times 1, or they could perhaps be 2x, or 4x times 1x, or 2x times 2x, right? There's a possibility of one or the other. Given this 21 here, it could be some form of 21 times 1 or 7 times 3. And one of my little guess and check method things really looks at this number 8. Not only the even odd thing, which we'll talk about, but also the size of it. If I used a 21 somewhere or whatever, I'd say that 21 kind of gets too large to be able to get me back to that number 8 somehow. So I lean more toward that 3 and 7 look, when I'm doing a question like that. So there's something to talking about there. But if I guess and check, let's try this. Let's put a 3 and a 7 here with like a plus and minus. I'd get, if I foiled this thing out, please understand that 4x times x gives me the 4x squared, and 3 times negative 7 gives me negative 21. But I need to really focus on this outside plus inside. 4x times negative 7 is negative 28. 3 times x is 3x. Negative 28x plus 3x is negative 25x. That's not negative 8x, right? So then, you can try and flip it around. Not the signs. The signs probably look good there. What if I put the 3 here and then the 7 here? This gets me negative 12x plus 7x, which is negative 5x. Closer, but still not the answer. And I spent time working on this 4x and x, trying to get these. The 21 and 1 won't work. Just kind of trust me on that right now. And I'll be honest, if I saw this for the first time, I would have told you right off the bat, 4x and x would not have worked here. Only 2x and 2x would have. And it has to do with this number 8 being even. Now, this doesn't always work for every kind of question. What it depends on is how the factors of your particular numbers work. 4 happens to have two different pairs of factors, either 4 times 1 or 2 times 2. 4 and 1 are even and odd numbers, and this is important. 4 and 1 are even and odd numbers. 2 and 2 are even and even numbers. And what happens is when you do your outside-inside thing, an outside plus an inside can either always add to evens or add to odds or whatever based on the kinds of numbers that they are. And whenever 2, an even number, multiplies with an odd or even, when it multiplies with an integer, it's always an even. When 4 multiplies with any number, it always becomes an even. And when 1, an odd number, always multiplies with some other odd. And this had to be odd because 4 can't share a common factor. I know I'm speaking above this, but I'm trying to answer the question. This would have always been an odd number. So going back to this 4x and x kind of stuff, check this out. Don't worry about what this number is, but 4 even times odd gives me even. Odd times odd gives me odd, and even plus odd equals odd. No matter what I do in trying to work factors of 21, which are all odd, and 4 times 1, even and odd there, I'm always going to generate odd numbers out, and the fact of the matter is 8 is not an odd number. And all I'm trying to say is that I would never choose 4 and 1 in this case because I always generate odd numbers out. It's kind of hard to answer this question without looking at this particular example for now, but the point is, I know that I'm going to use 2 and 2 in that case because it'll give me an even number plus an even number, which is even, right? It works it out. And it just so happens you can use negative 7 there and positive 3 to get negative 14x plus 6x, which gives you that negative 8x. This doesn't always work, but the general idea behind it is when you have an even linear coefficient right here, that comes from some even plus even set. And when you have an odd linear coefficient, that comes from some sort of even plus odd set, or odd plus even, depending on how they work. Now, there's the odd plus odd case, but I'll tell you what. Now, odd plus odd is even, but I'll tell you what, that only happens when this is already odd and this is already odd, and there's nothing else you can do to reduce that more, because odd numbers, odd coefficients and constants always only come from odd factors. So there's nothing for you to reduce from that, right? Meanwhile, if this was that minus 5x right here, this minus 5x just like this right here, suddenly I wouldn't ever choose the 2x's and 2x's, because these would only give me even sums, right? Even plus even is even, whereas this would give me even plus odd. So the whole gist behind it is, when you look at your linear term, you look at whether it's even or odd, and you can ask yourself whether the factors of your first and last terms can generate different kinds of pairs of numbers, all evens or some mixes of evens and odds, so that it mixes up your set. If this number here instead was a 10x squared, that doesn't help me out much, because your factors are either 10 times 1, even times odd, or 5 times 2, odd times even. That's not breaking up the scenario of both of them are even or something like that. Unless this back number is some form of even numbers there, but then it might have a common factor with the 10, you know. So if this was all even numbers, if this was a plus 24, I don't know how to factor it right here because I'm not working something out for sure. But if this was a 17x and all that, I don't know if this factors. I'm not going to try it. But you know, 24 being having some evens with odds like this, but also having some evens with evens like that, an even with odd there and an even with even. I know that I can weed out the 12 times 2 and the 6 times 4 for several reasons. One of them being, this is an odd number, and I always have to multiply. I have to generate this from an even times an odd, and if they were both evens here, I'd be doing an even plus an even somewhere. So that wouldn't really work. The other thing is, one of these would fall in with a factor with 10 or 2, which are even numbers, means greatest common factor, so it wouldn't work. So I know that only 24 and 1 or 8 and 3 would work, not that it necessarily works in this answer. Anyway, so I don't know if I'm answering this really in full, and it's kind of hard for you guys to respond back when it comes to this, but the general sense is, what I'm doing is I'm trying to reduce the number of guesses I have to do by understanding that this number is a sum of either even, even, or odd, even, or odd, odd, but then I'm not reducing anything. And then based on that, I got to decide, and this is all through number sense, do my factors here or here generate me different combinations of some even evens that I can either weed out or absolutely must go to, right? That's the general gist behind it there. If you see some of my things in videos and see as I work them out, or ask me for more examples of problems, I can do a lot more and just play with that. Boom, boom, boom. But I'll tell you what, there's overlap between that even odd stuff and that whole greatest common factor stuff. So sometimes it's like I can't put an even number with an even number in a factor, because that means I could at least factor 2 out of it. So anyway, I don't know if that answers that in full. I try and do the best I can there in talking about it, but I hope that at least makes a little bit of sense. You probably need a lot of examples there. All right, let's go further. Can perfect cubes be broken down further than the format of a plus b times a squared plus ab plus b squared? One quick fix on this thing here. They're talking about a sum of 2 cubes or a difference of 2 cubes. I'm not sure which. Let me write them both out for you. They're talking about the a cubed plus b cubed that equals a plus b times a squared minus ab plus b squared. I believe they put a plus here. That should be a minus. But the a cubed minus b cubed is a minus b times a squared plus ab plus b squared, like that. So 2 different factorizations there. I don't know which one they were going for, but some are difference of 2 cubes. Their question, and it's interesting because I said questions are asked and answered the order which they're received. I opened this form up yesterday, and then yesterday meaning the 24th of August. Today's the 25th of August when I started talking more about this, and I answered their question in class. Maybe they asked this before I answered it, and I like that they asked this kind of question. It's a really inquisitive kind of mindset here. They're asking, you know, we're factoring this sum of 2 cubes, difference of 2 cubes into this factorization here. Their question is, can this quadratic be factored down further? Can this quadratic be factored down further? as long as we're talking about cubics here and x cubed, whatever, the answer is actually an emphatic no. And it's a really good question to ask because we've been factoring quadratic trinomials. So why is it possible that we can factor these ones down more? It is an emphatic no. Not only is it not factor, and when I say factorable, I mean with real integer coefficients. Real, a 2, not a 2i, right? Not imaginaries. But here's the thing. Not only is this not factorable, in the quadratic formula, if you try to solve this as a quadratic, set it equal to 0 and find its solutions, the solutions are always complex solutions with imaginary components. They have I in it. They're imaginary solutions, which means not factorable if the solutions are also imaginary. If you kind of want proof to that, I don't know if I want to spend time on it. I could talk about the discriminant, do my b squared minus 4ac discriminant portion. I should probably do that in my class. And show you that discriminant is always negative when you use the b squared minus 4ac. It's kind of an interesting bit there. We can try it with an example. I'll show you with this thing, but an example doesn't prove it. An example just kind of gives the idea here. If we had, what's a perfect cube? 8x cubed minus, I can't use 64, 125 right here. This would factor into 2x minus 5 because that's a perfect cube there. And then this is, you square the 2x to get 4x squared, plus you do 2x times 5, which is 10x, plus 5 squared is 25. So there's the factorization, and the question becomes, is this further factorable right there? Well, it's not. It's not. But if you did your b squared minus 4ac, 100 is b squared minus 4ac like that. This becomes 16 times 25, I think is 400. So 100 minus 400, which is negative 300. That's the thing inside the square root in quadratic formula, and square root of a negative leads to an imaginary or complex solution there. So you always get a negative discriminant out from that thing. It's not right for it. And it's interesting because it almost takes on the appearance of a perfect square trinomial. It's almost that 2ab, but that 2ab does a lot to your number there. So no, it's a good question, but the answer is no. It's actually not factorable further as long as we're just talking about cubics there. All right, next question. Will there be a question that is not factorable? Will they be on the test or quiz? If so, when there is no answer to the problems, what should we write? And is there any way that we could double check to make sure there really is no answer? So when I first was reading it, it kind of teetered on curriculum based more than content based. So I just wanted to say with you guys again, I want to for these kinds of questions, I want to try and make sure that they're based on content. But it looks like you really got to content based. So there are things that are not factorable. They're just considered prime polynomials that way, just like 2 is a prime number because you can't factor it down more. They'd be considered prime. I think for the most part, when it comes to, I'll still answer it, when it comes to us trying to quiz or assess you, we're probably not trying to make them not factorable because that means you have to exhaust all options unless those options are very minimal or you can strategically work out which ones to ignore outright because we talked about the even odd thing and things like that, or numbers that are just too large and small. But the question then comes, what should we write if that's the case? If I just made one up right here, let's make one that's clearly not factorable here. I'll make it really easy with x squared. X squared plus 2x plus 8. 8 is either 4 times 2 or 8 times 1, and 4 plus 2 is 6, and 8 plus 1 is 9. This number would have had to have been a 6 or a 9. This is not factorable. There's no factorization to this thing. So you can either write not factorable, or the kind of mathematical term we could say there is prime. It is prime in that case. So either one or the other is what you would put. Now the other part of your question was, is there a way that we could double check to make sure there's no answer? I mean, in this case, you're exhausting all your options just for a 1x squared. You're exhausting what are your factors of 8, 8 times 1, 4 times 2, and say is 8 plus 1 equal to 2, is 4 plus 2 equal to 2. If those don't work, then yeah. To double check, you have to kind of exhaust all options. I mean, all, again, viable options. With that whole even odd thing, I won't try 4 and 1 if my thing adds to an even, like, you know what I mean? So you only exhaust all options that are available to you. And once you've exhausted them all, then you're absolutely certain. So no other way there outside of, using photomath, taking a picture or something like that and having it tell you. But no, not necessarily. You got to try everything within realm and see if they work or if they don't there. But it's a good question, and I don't believe the goal is to make things not factorable for you guys. It's to say, but that's my mental factoring guess and check thing is always assume it is factorable and get started on it and try and see. If it's not, if you tried everything, then it's not factorable, then we'll just move on. That's kind of it. Okay, the next question. Will there be a polynomial unit test or just a quiz? So that's curriculum based. I'd rather not answer it, but I will. There will definitely be a test, but there's more to do. We're going to be talking about, I got to check the units actually for sure, but we're going to be talking about division of polynomials. And I think we're getting here into what's called the rational root theorem, which actually involves solving with solving some things. So the rational root theorem is involved. And I don't know if it's this unit or not, but we're going to be dealing with polynomials for about 3 straight units in this semester here, and we'll be graphing polynomials. What was the other thing I was going to say that we're going to do? Factoring, solving. Maybe some more things on solving them, but the rational root theorem is a big part of getting certain solutions out from it. So, will there be a polynomial test? Yes. All right. What is our test on that is on Monday? So again, curriculum based. What is our quiz? The quiz is on. If we were to go backwards here, let me write them out. Let me type them out here. Give me 1 second. It's on, so everything polynomials based we've hit so far. So we started with, we're not going to name them, so to speak, in them, but, make sure that you're combining like terms. You're simplifying by adding and subtracting. So add, subtract polynomials. Then we multiplied them. Multiply, distribute polynomials, whether it's FOIL or whether it's a 3x3, 2x3, stuff like that. And then we got into factoring a bunch of different ways. We factored basic, factoring when a equals 1. We factor, hold on, let me do a bullet point of these ones. We do when your quadratic coefficient's 1. We do it when it's greater than 1. And assume, GCFs. Oh, GCF factoring always. Well, GCF's a part of it. When a is greater than 1, we have some special cases. Difference of 2 squares, perfect square trinomials. We have some cubics. We have sum and difference of 2 cubes. We've done some factoring by grouping. And by the time you see the video, you'll probably have run into these. We're going to do things that are in quadratic form, but higher degrees. Higher degree in quadratic form. Quadratic form means it's a trinomial. Maybe. It could be a difference of 2 squares. But it's a trinomial set, but that maybe an x cubed is being squared. Or an x to the 4th is being squared. An x to the 4th to the first power and things like that. So those are the ones there. And, of course, with the multiplying polynomials, there's also expanding, binomial expansion. Remember Pascal's triangle? So binomial expansion also takes place, a plus b to the 7th power, big things like that. So those are the different kinds of things that we will hit in that. And a lot of them were from integrated math too. This one's new, right here. And then these ones are new right here. That's it. The other ones are of old. Maybe you're learning new processes, but the other ones are from integrated math too. So good refresher. But then we're going to hit polynomial division, not in the quiz, but polynomial division, long and synthetic division there. Rational root theorem, which is IM3. I didn't get to teach rational root theorem last year. I'm excited to do it this year. And yeah, so we'll keep going with that there. Okay, how close is the IM3 curriculum to the IM2 plus curriculum? Another curriculum-based question. Guys, this is based on, I want you to ask content-based questions on polynomials, things that I can help you address polynomials more. I don't teach IM2 plus, so I can't say. I would say that IM2 plus is closer to IM2 because it's IM2. If you're asking IM3 and IM3 plus, they go faster, they demand more, they have harder questions and numbers and things like that. I'm not sure. There's a curriculum there where they expect you to just be on your stronger case there, bigger workload. I wouldn't say IM3 is close to IM2 plus curriculum because IM2 is IM2. So anyway. All right, how many questions, guys? How many questions are usually on the test? I couldn't say for sure because to me, factoring is pretty fast, but there can be different kinds of questions. The binomial expansion might take a long time for some people, things like that. Every test is different. You could have a 6-question test for all I know, all depending on what it is, and you could have a 30-question test. It depends on how much is drill and kill or not. So I can't give you a usually. What I can say is we are time conscious with things. If we give you the hour is what you get. Unless you have some sort of accommodation kind of thing. Anyway, I'm not going to stay long on that one because it's so dependent, whatever. I can say that the quiz, I was looking at maybe 10 or 11 questions for the quiz, but that's with adding and subtracting polynomials, quick basic factoring, some special cases, a binomial expansion question, things like that. So you can say just then. That might seem like a lot of questions to you. Is there an easier way to factor cubic expressions? I don't know when the question was asked, so I don't know if you're talking about factoring sum and difference of two cubes, or if you're talking about factoring by grouping. I would say no to both. There's really no easier way. I'd say what you got is really the best option. I mean, when we talk about, let me just write this out, sum of two cubes again. When I'm giving you this factorization, I mean, that's what a sum of two cubes factors to. That's the idea. This isn't calling it easier or harder. That's what it factors to. That's the factorization. That's the breakdown. And remember, this quadratic doesn't factor more. So I mean, there's no easier or harder way than that. That is just what it is. If you're talking about recognition of what is a perfect cube and stuff like that and whatever else, I'd say what we were doing has been pretty good, especially when I say, hey, there's that's what we do with it. If you're talking about factoring by grouping with the quadratic things, when we have, we're talking about a quadrinomial like this one right here, and then we kind of pair things off and factor by grouping. Once again, kind of, I'd say what you were doing right now is really the best approach, because it's taking, we're always doing the opposite of distribution. And in this case of distribution here, because there are four terms, and pairing them off, we are finding the greatest common factor of both sets, and then what is identical in there is the factorization that goes into the factoring. Literally that factoring answer, this thing right here exists as a common factor for both. You understand what I mean if you've done this. If you haven't, maybe you don't. But no, what you're seeing is really the best thing. Maybe you're asking because you've learned different strategies for factoring quadratic trinomials, and I get it. Quadratics, the more complex you get, the more restrictive you are in ways of doing things. I'll say that. And once we hit cubics, it's more complex than quadratics in that way that there aren't really a lot more methods. I can't really think of many that other people would do, and I can't really think of being able to skip that step in between. You really need it with the greatest common factor thing. I'd say what you have is really the best stuff. If you find anywhere online that shows any better or different, let me know, but everyone's going to teach you that way. When it comes to quadratics, though, like I said, you can factor by grouping with quadratics, whereas I go mental factoring. People do different things with what's called a generic rectangle. I know that one of the other teachers does this like slip and divide thing, kind of creating fractions. I'm not going to entertain it. But anyway, so, just a bunch of different methods for quadratics. Cubics, no, that's kind of it. I wouldn't do any different. All right, next question. Can you explain the process of eliminating factoring options based on odd and even numbers again? So I answered that at the top. It was the very first question, and I don't know if I did it very well. I explained a lot there. What I will break down is this. This will be a little bit different here, just to write it out. It is based on, in FOIL, it is based on the outside and inside part, right? So it's based on when you have your sets of factors. Let's say it was just a plus b and c plus d. It's based on the linear term being this outside multiplied plus the inside multiplied. And when you multiply an even number with an even number, you get an even number out. An even number with an odd number, you get an even number out. And an odd with an odd, you get an odd number out. And then when you add evens, you get even numbers out. When you add an even with an odd, you get an odd number out. And when you add an odd with an odd, you get an even number out. So the reason I bring all this up is because in the FOIL aspect, when you multiply, if a and c were both even numbers, straight up, once you multiply an even number with something, you get even. And you know what happens when you add an even with an even? You get an even. So the whole idea is, if you have an even linear coefficient, you know that has to come built off of either two odds added together, which means there's nothing to reduce because odd numbers come from odd factors only, or they would come from factors of your number, if it was a 4, an 8, a 16, whatever, where you got to get the even factors in it. You have to choose the even factors, the 2 times 2 or the 4 times 2 or whatever, and start working that out there, unless your last term can do the same thing. You got to pull those things out from it. Otherwise, if your linear term's an odd number, you got to make sure that when you multiply this and plus multiply this, that one of them's odd, one of them's even. So you can't have 2 even numbers here and here. You can't have 2 even numbers here and here. And you're eliminating, the whole idea of it is you're eliminating maybe up to half or more, half the things you got to try. So I'm not going to explain too much with examples. I did one of them in the thing, and you'll see some things with videos. But you're eliminating the things you got to try. Why do I got to try, again, 4x times 2x here, when I know that the things add to an odd number, so I know I should be doing 8x times 1x right there. Because now, again, even plus an odd, and that gives me an odd. And that's kind of the idea behind it. I'm saving myself from trying things that I don't have to try. Same thing with when we talked about different sizes of numbers and stuff like that. I saved myself from trying something too big or too small. And that's kind of just the basic gist of it there. All right, thanks for asking the question, though. All right, next question. How would one factor a 5-term polynomial, if that's a thing? That's a good question. So we just talked about factoring cubic quadrinomials or quadrinomials using factoring by grouping. Now, what I mentioned was it works really well with even-termed polynomials, 4 terms, 6 terms, 8 terms. The main reason being is, assuming a binomial is one of your factors, when you pair them off and find the greatest common factor of all those, there exists a binomial within on all those, and then if they're identical, you can factor it out. A 5-term polynomial is a little different because, like a quadratic trinomial, 2 terms are going to have to combine somewhere. Because if you think about this right here, in a 5-term, let's see, how do I say this best? If I multiplied a binomial times a binomial, a plus b and c plus d, and if they didn't combine when you FOILed out, you're going to have 4 terms because this is a 2 by 2, right? 2 times 2 equals 4. If they didn't combine. If you have a 2 by 3, a plus b times c plus d plus e, and if terms didn't combine here, that's not always the case, but if they didn't combine, you'd have 2 times 3, which is 6. You'd have 6 terms. You would have to have some sort of thing, which happens often. You'd have to have some sort of binomial times trinomial where 2 terms only would have to combine. And I don't know if I can make one up for you. I don't know if I'm savvy enough to do that. I think something would have to be a cubic. So let me try this. You would have to have something like x plus 2 times, I'll keep the numbers small, x, I think, cubed plus x squared plus 3. Let's see if that'll work. If I distribute that, again, x to the 4th plus x cubed plus 3x plus 2x cubed plus 2x squared plus 6. It starts off as 6 terms, but I can combine the x cubed here and the 2x cubed here. So I'd get x to the 4th plus 3x cubed plus 2x squared plus 3x plus 6. So if you're asking, can you factor a 5-term polynomial? I can tell you yes. And the reason is because this factors to that. But did you say can you or how do you? You asked how would one do it? So understanding that it factors to it, as you notice, a 5-term polynomial had to originally be 6 terms. 1 term had to combine, and then it turns into this set right here. So what you would have to do is you would have to come up with, oh man, I don't do this very often. You would have to come up with pairing off things the right way, because it's not as easy as a quadratic trinomial to actually split it up into this first and then pair things off that way. You'd have to come up with, within here, some sort of common factor thing that you can pull out, and then within that pull out, you can find a common you can share a common fact within. I'm trying to see if I can find it. Sorry, this is kind of on the spot. X squared. I don't know if I can come up with it on the spot. I think, well, the basic gist of it is I'd have to come up with getting this out by pairing up the right terms. X to the 4th, 3. Ooh, I don't know if I can do this. I'm not very good at this. You'd have to find a way to split things up the right way. That's all I can say. You'd have to find a way to split things up the right way so that they factor out into sharing a common factor of an x plus 2 somewhere. I don't know if I can do that very well for you. It's possible. It's possible. It's not easy. If you could find a way to split this up in the way that you had the 6 terms there, it's very easy from the factoring by grouping, pair off terms. Otherwise, somewhere here, you can probably get a binomial, trinomial, factor things down, and you'd be on your way. I don't think I can do that for you. I don't know, especially since I made up that problem on the spot. It's possible, but you can see where a 5-term polynomial comes from, and you can see why even-term polynomials work a lot better, pairing them off, because it comes from a 2 by 3 or a 2 by 2 or something like that. All right, and this is the last question right here. When factoring by grouping, can you use the even-odd method to find the number of terms that can be factored out to make the problem easier for using bigger numbers, or can that only be used when working in quadratic trinomials? The even-odd thing is, so factoring by grouping has to do, when we were doing it, unlike the problem I just talked about here, which was not very conducive to what I was talking about, when we factor by grouping in a cubic quadrinomial, none of those terms combine to anything, right? So when we talk about factor x squared plus 5x minus x cubed minus 5x squared plus 5x squared minus 4x minus 20, I think would work out there. Nothing combines here. So the even-odd concept has to do with the fact that two linear terms would combine compared to that of talking about x squared plus x minus 20. Notice in this one, this x is a combination of 5x minus 4x, right? We had to combine two numbers to make this number here, and this number being odd was a result of being an odd plus an even, or odd minus an even, whatever it is. This doesn't have a combination of two numbers to worry about that concept. And there's nothing you need to really guess in this way. The distribution into a cubic quadrinomial came from a common factor existing within these two guys here. If I factor x squared, I get x plus 5, and I factor negative 4, I get x plus 5. This x plus 5 existing as a common factor in both those guys right there, and you get x plus 5 here. Here you get x squared minus 4, yada, yada. By the way, difference of two squares gets you x plus 2 times x minus 2. Times x plus 5, that's the answer. But no, there's no even odd thing you have to worry about in that case because there's no combination of numbers, right? No like terms combined there, unless you talk about that 5-term one I just talked about, in which case there might be some even odd thing to get to. I don't know how I could work that one out. I probably didn't give myself a very easy problem to do on the question before that. I apologize there. But yeah, no, there's nothing you have to even, you can't use the even odd method because there's nothing to combine. So you're all good there. All right, and that ought to do it for this one here, guys. So there were the 11 questions. I hope they were kind of helpful for you figuring things out for your quiz. Maybe I overspoke on some things, but it's more of a power half hour for you guys. Thank you so much for watching, and take care. I will see you in the next one.